And our goal here is to just review for our final exam coming up on Thursday. So it's our last class, last official class period. We don't have a class period after this one. We just have, we take the exam on Thursday. Now, let's try and talk about course outcomes. Let's see if I can zoom into this. Here we go. Right, so this is a comprehensive final. Anytime you have a comprehensive final, what I find is if the syllabus is well written, these course outcomes are incredibly important, and especially if you're taking a comprehensive final. Just as a student, these are one of your best tools to go through and study. And if you read through those course outcomes and any of that is like, Steve, I don't know what the heck that's saying, that's kind of a problem, because it's basically upon, you can read this is upon successful completion of the course, students should be able to. And so if you're taking a comprehensive final, you should be able to do all those things. And this is a comprehensive final. You guys have seen how everything in this class, this class is kind of like statics. There's a few classes that you guys will take where all the material builds on itself. There's very little we do at any point that we don't use them later. It's kind of fun to teach these kind of classes, but it's definitely a bit of a challenge too, because that means we've got to get everything right as we go. I think we've done okay with that. So let's look at these. Upon successful completion of the course, a student should be able to utilize various methods, including tabular tables, graphical. We didn't talk much about using graphs, using Euler diagrams. If you had to, I think you guys could probably figure it out, but you're capable of using tabular and specific heat content for determining state properties and changes in state properties. We've accomplished that, even if we didn't do the graphical version of them. I don't think that's necessarily necessary since we're so good with tables at this point. Number two there, solving problems involving boundary work, RESTful systems. So we've hit on boundary work throughout the semester. That even showed up still in chapter 9, looking at auto cycle problems, right? So all the way up to the very end, we're looking at systems where volume's changing, therefore there's boundary work occurring. That's the fundamental basis of thermodynamics. Honestly, it's the fundamental basis of our society, considering the impact internal combustion engines have. Number three, simplify general expressions of the first and second laws of thermodynamics to an applicable version for any closed system or steady flow control volume. That was our focus in chapter 2. That continued into exam 2. That was our focus in exam 2, is being able to do that for any system, simplify first law equation. That continued into exam 3, where we continued with the first law and then we expanded into the second law. So we've done that. And then also number 4. So 3 and 4 are really kind of the whole fundamental basis of this entire course. Take general expressions of the first and second law, simplify them to an applicable version for our situation, and then apply those in conjunction with other laws, principles, or in this case, property tables as well, to solve for an unknown value. So it's really kind of, like I said, 4 and 5 is really the whole goal of the entire course, to be able to do those 2 things. The others are important, but if you can do the others, they tend to contribute to those numbers 3 and 4. And then we've finished out the semester looking at some ideal cycles. We looked at the Otto cycle. We'll discuss the diesel cycle and the Rankine cycle just briefly today after we review. And that's it. I mean, that's essentially the entire course. So that's always where I like to start out when we review for a final exam, for a comprehensive final exam. Let's go look at those course outcomes, make sure those are clear. So as you read through those, if something there is not clear, that tells you probably where you want to start studying, and that also probably tells you what questions you need to be asking me at this point to kind of direct you where you want to go. So again, final exam. That's going to be, if today is the 26th, it's going to be Thursday, the 28th. You get a little longer on the final and you do the other exams. It's scheduled basically from noon to 1:50, so just shy of 2 hours. It's the same 1 hour and 50 minutes everybody that's ever taken one of my finals gets. So that's just kind of our scheduled time. If you can't make that time, you let me know just as soon as you know. Okay, we'll figure something out. Let's try to be there on that time. What else we got here? So again, it is comprehensive. All right, that's for us. That's chapters 1 through 7, essentially all of it. And then also 9, specifically the Otto cycle. I'm not going to test you on the diesel cycle. We'll discuss it briefly today. So we're not going to do anything, but you've got homework out on the Otto cycle, so that will show up there. Also, you can omit unsteady flow. Mentioned when we talked about unsteady flow, that would not ever show up on an exam or final. We just talked a little bit about using uniform flow assumption as at least a possible way I could estimate unsteady flow outcomes. It's a nice thing to talk about, but that's not going to show up on this final exam. Isentropic efficiency, right, and the Otto cycle. Those are 2 new topics that show up, but then everything we've talked about on all 3 of the other exams are fair game. You'll get standard rules, 1 sheet of notes, front and back, up to 8.5 by 11, whatever you can physically write with your hand, I'm okay with. What else here? Open book, mostly because you need property tables, but if there's other stuff in the book that is helpful to you, I don't mind you using it. Just as you guys have probably already figured out, if you're flipping through the book to try to find the one example that's just like the one problem in front of you, you've probably studied incorrectly. You can do that. That's better than nothing, but it's probably not the best strategy, assuming we're going to find an example just like the one problem in front of us. Anyway, what else? In calculator, we've talked about calculator use. Too concerned at this point, but as long as your calculator does not freely access the internet sitting there on the table, as long as I don't think you're scrolling through PDFs of solutions manuals on your calculator, you should be well just fine. So logistically, the final exam looks just like the other exams. There is one small difference because you get a little more time. What I do is I put 5 problems on the exam. They are 25 points each. And so what that means is I only grade 4. There are 5 problems on the exam. I will only grade 4 of them. I will only grade your 5th problem if, let's see, what's the best way to put this? Place X or leave blank any problem you wish to skip. Now, in theory, you could do that to all 5 problems. You're not going to be happy about your outcome, right? I'll grade the first 4 problems, basically, no matter what. But if you want me to grade your 5th problem, if you go through, you flip through, and it's like number 2, just you got no idea on number 2. I'm going to do number 5. So just put a big X on whatever you've written down on number 2, and I'll skip it. I'll grade it. I will not grade. I've got a system where it's like if you've X'd out a problem, then I put like a check mark or something like that on the 5th page that tells me, okay, go ahead and grade that 5th page when I get to it. No, it's not. I'm not going to grade all 5 problems and give you the best 4. Tell me which one you don't want to create. Skip it all together and leave it blank, or put a big answer on it. Make sense? Questions there? Okay. So if you're like, Steve, I'm just not going to work an auto problem on the exam. It's fine. There's an auto problem on the exam. Now, if you think back to, and I should have mentioned this when we worked the big auto problem that took out two entire boards and was really cramming in to get it all in there. That's a problem where we've asked you to find like 5 different things and have to get to all 5 of those different things. It's different for each one of those. If I'm careful about what I ask you, and you know your way around an auto cycle problem, we work with class, I'm going to ask you to work on your homework. If you do at least 1 or 2 more in practice, then you're gonna have to be very comfortable with the mathematics associated with that cycle problem. If you reach that point, then if I ask you some very targeted information, it's not too hard to get to, given what I've given you. Those problems really aren't. They're not as daunting as the one we worked on before. That's kind of the best way to put it. So don't just let what you've seen so far completely scare you off the possibility of that being a problem at work in an exam scenario. Those problems can be structured in such a way that they are perfectly doable on an exam. Again, I'm going to ask you to work 4 problems. You get a little more time than what you normally get on a regular exam. Yeah, you do have to make a decision of which of the 5 problems you want to work 4 of, so you do get a little more time. Anyway, and you guys know how I grade. Show me you know how to solve the problem. That's worth way more points than actually solving the problem, because I'm aware you don't have infinite time. Okay, questions here so far? Like I say, logistically, my goal is it looks just like the other exams. The main 2 differences, time and this whole, you get, here's 5 problems, work 4. All right, so if we then review of topics, by the way, any particular problems or homeworks or examples that are just destroying and you just they occupy your nightmares, and you really want, let's hammer them out and try to look at them and figure them out. Anything like that burning for you guys? If something comes up, say so. We'll look at it. Okay. Otherwise, we'll just kind of go through a skeleton outline of the topics that we've discussed throughout the semester. Now, yeah, there's chapters 1 and 2. They are relevant. They are important, but not going to be any chapter 1, 2 type problems on the exam. Right? Not even a chapter 3 alone type problem. There's plenty of chapter 3 built into any problem involving water in R134. We've got to be able to use the property tables. Right? So using property tables. And we outlined, it's been a hot minute since I've written this down. I probably messed it up, but we outlined a process for doing that. You know, basically is identify your substance. Right. Number 1 is identify your substance. Number 2 is basically record known properties. Right. And so using property tables, which really it's more finding unknown properties. That's really kind of our goal. Initially, we said, well, using the property tables, here's the process. But really what it is trying to find an unknown property. What's the process? The process is the same. Number 1, what's your substance? What is your substance? And that'll tell you what model we're going to use. Are we going to use tables? Are we going to use some kind of ideal gas model, right? What is my substance? And then make sure I know what properties I have available, right? And then step 3 kind of branches out. You've got the water in R134A. You need to, step 3 kind of falls into this category. Determine the state. is really what it is. Right? Determine the state. And that basically means what table, what row, if we're using tables. Or what is it specifically that I need to know about this substance at this point to determine other properties. For water in R134, you have kind of two main scenarios. You're given pressure or temperature. You can plot that on your y-axis, and then you're given V, U, H, or S. You can plot that on your x-axis. And then you've got the dome region, the saturated dome region. And basically, we need to know, where do we lie? Where is our state lie on this diagram? And if I'm giving, there's a variety of properties. I could have pressure or temperature, specific volume, internal energy, enthalpy, or entropy. And given, this is one possible combination that can be given. So there's one of these two and then one of these four. And given that combination, well, does it put me out here in the superheated vapor region? Am I in the saturated region? Is it maybe a mix? Or am I over here in the compressed liquid region? How do I know that? Well, at the given pressure temperature, I need to go look up the values for saturated liquid and the values for saturated vapor. And where my VU or H or S value lies in relation to the saturated liquid and the saturated vapor value, that'll tell me where I am on this diagram. The other possible combination I might be given is given pressure and temperature. And instead of seeing this as a dome, here I see this as a curve, right? And everything to the left of the curve is liquid, and everything to the right of the curve is superheated vapor. Right? What I normally do is, given the pressure, I go look up the saturated temperature. That's the boiling temperature, if you will. And I see, okay, well, am I at or have I exceeded the saturated temperature? If I've exceeded the saturated temperature, that tells me I'm out here in the superheated vapor region. It's like water at 1 atmosphere. It's anything over 100 degrees C, right? At 1 atmosphere, water has a saturated temperature of 100 degrees C. Anything more than that puts me in the vapor region. Anything less than that puts me in the liquid region. Now, for ideal gases, we know this, PV is equal to RT. So that will relate PV and T to each other. So that means I just need two of those properties to find the third. And here's what we also know. U and H are functions of temperature. So that means to find U and H values, I just need to know the temperature value. That's it. And for S values, really, it's going to be change in S values is what I'm actually after. So let's say delta S. For delta S, we're going to use Gibbs equation. So those are the tools I've got for properties for an ideal gas. If it's water R134, we're just going to use property tables. Now, and we've discussed before, if I know I've got a liquid staying a liquid, so if I've got liquid water staying a liquid water, or if I've got a liquid, if I've got water vapor staying a vapor, if the phase is constant, I can also use specific heats. And we've discussed that pretty in depth. So we'll see that a little bit later. I guess we could discuss it now. Actually, we can discuss it now. So we talked about specific heats. Again, if phase is constant, well, how do I know that? Well, you need to know the state of your system. That's step number 3. Right? You know the state of your system. So don't use specific heats for something like water R134, where there's a good chance it could change phases on you. unless I know specifically that it's going to stay liquid or it's going to stay vapor between the states. But for ideal gases, so this works really good for air. It's not going to liquefy on us under standard conditions. For ideal gases, C sub V dt is equal to du. And what that means then for us is that delta U, U2 minus U1, is equal to this integral from T1 to T2 of C sub V dt. And what we normally do is we approximate that as C sub V at the average value times the change in temperature. Oh, sorry, I'm off screen. Right. So again, C sub V represents a change in internal energy. On a differential scale. If we integrate that, that's fine if I can assume that C sub V is reasonably constant, and that's normally a fair assumption over a small enough temperature range. We just use the average temperature to find C sub V average. We can do the same thing with delta H. C sub P dt represents dH, change in enthalpy. And so H2 minus H1 is equal to the integral from T1 to T2, C sub P dt. And again, what we normally do is, I mean, you could go look up C sub P is a third, we have models for C sub P as a third order polynomial as a function of temperature. It's not hard to integrate. I haven't asked you guys to do that. I don't necessarily see a lot of value in it because honestly, unless you're going to program it into a computer, it would mess with it. Because it's just as reasonably accurate as we've seen more than once to get a good C sub P value at the average temperature. Assume that it's reasonably constant at that average temperature, and then just simply multiply by the change in temperature at average C sub P. And that'll give you a really good approximation for delta H. Again, what are we trying to do here? We're saying finding unknown properties. Here's how you go about it, right? I'm using property tables. I'm using for water, R134, any other substance. Make sure you know where your phase is. And once you know your phase, then you can go to the specific row within a specific table and record values. If I don't have tables, or if I want to use something else, specific heat is a nice tool for determining delta H and delta U if I know my phase is constant, especially for an ideal gas. Right? For solids and liquids, again, that's a solid staying a solid or a liquid staying a liquid. I can also use specific heats there. Your text likes to use C sub P dt to represent du. A lot of texts will just say for solids and liquids, there's no difference between C sub P and C sub B. So they'll just say C. Your text likes C sub P. That's fine. So again, delta U then, because C sub P is going to be reasonably constant, we just say it's approximately C sub P delta T. And that'll get us an approximation of delta U for solid staying a solid or liquid staying a liquid. The temperature is going to be the driving force there. A lot of times temperature is going to be the driving force for change in internal energy and enthalpy. When the phase changes in substances like water or any kind of refrigerant, pressure can play a bigger role. But a lot of times that temperature is the main driving component for these problems. Now, what else we got here? And we did talk about, just kind of mentioned briefly, we talked about interpolation between rows. And then we did also talk about if it is a saturated mix, what do we do, right? So outside of that, for saturated mixtures, really saturated anything, we can use what we call the X value. The X value is the quality. Don't use the X value for anything that's not saturated. Doesn't make any sense. But what the X value represents, we often refer to it as the quality. It represents the portion in the vapor phase. How much is in the vapor phase? How do we find? Well, X is equal to, we could start with a specific volume, that specific volume value that's known or given, minus the specific volume value for saturated liquid, divided by the difference between vapor and liquid. And that's equal to then the same ratio for all the other properties. U minus U sub F. Remember the UFG value represents the difference between UG and UF. You can mathematically take the difference if you like, but if your property table gives you that value automatically, feel free to use it. Same thing for the other properties. H minus H sub F over HFG. It's also equal to S minus S sub F over SFG. Again, that's what we do if we're in the dome region. We need to know how far are we in the dome. Are we closer over here to the G, or are we closer over here to the F? The closer to G we get, the closer this X value gets to 1. Notice if V is equal to VG and X becomes 1, that means it's 100% vapor phase. If V is equal to VF, it's saturated liquid, you get an X value of 0. Anything outside of 0 to 1 doesn't make any sense. We only use it for saturated something. Okay, so if I continue on my list up here, so we said identify my substance, record known properties, determine the state, right? A variety of ways we can do that. And then once I've got a handle on that, if I go back, then step 4 is record your desired properties. Right. Once you've recorded the desired properties, then step 5 is profit, conquer the world. Let's just say solve the problem, because I can't spell. Because again, property, as we've seen here, as we've seen since exam 2, finding property values is just a sub problem within a bigger problem for us at this point. So it's just allowing us to solve for some unknown that I need to solve the bigger problem. Right, and once we've got a handle on finding properties, then we can start talking about the laws and relationships that we need to plug those properties into. We've already mentioned the ideal gas law. Anytime I'm dealing with substances, can be, I'm going to expect to be in the gaseous form. Ideal gas law is just fine. Air is the common substance that I would probably put on the exam. Now I'm going to tell you there's no solids or liquids because I can't make that promise. I've not finalized the exam, so I don't know for sure what substances are on there. But I expect a lot of water, R134, and air to be on there. But I can't say it's those are the only substances. So once we've got that in hand, we have an idea how to find unknown properties. And again, you look back at those learning outcomes, and the goal is to be able to simplify both the first and second law. So if we start talking about the first law, we start talking about the first law simply tells us that energy cannot be created nor destroyed. It can only change forms. Now there's a variety of forms. But what we know is the total rate of energy in minus the total rate of energy out basically equals the rate of energy change for our system. That's dE system dt. We've said multiple times, this is simply the idea that in minus out equals change. And that's true for any conservation law for the most part. All conservation laws can be written with some version of this way. So if we think about it that way, then we get into, okay, well, what are the types of energy that can come into the system, right? Types of types of energy that can come into the system are heat, work, mass. And the types of energy that can change are going to be internal, kinetic, and potential. So again, what we're saying is if I add or subtract, if I find the net rate at which these different types of energy are coming into the system, that's going to equal how the energy for my system is changing. And those types of energy can be internal energy, kinetic energy, potential. That's the first law in its purest. Now, not expecting you to do anything useful with the differential equation. Let's talk about how do we get this down to something that we can work with without a real in-depth understanding of differential equations at this point. Just a basic understanding is all we're asking of. Well, one of the common scenarios we can run into is for closed stationary system. So we're dealing with a closed and stationary system. Well, if it's a closed system, that means there's no mass crossing the boundary. So there's no mass energy crossing the boundary. If it's stationary, the kinetic and the potential energies are not changing over time. So I'm really left with only the internal energy. We'll see that when this shakes out. So here's the thing. If I'm dealing with a closed system, I'm probably not so worried about every little differential change over every differential time frame. I'm probably more worried about a total energy change for my system over a total time period. And I'm probably really not even concerned about the time period. What I'm really concerned about is the total amount of energy. So if I move delta T over here, and if I say, well, if I take the amount of time over which this occurs, multiply that by the rate of energy transfer. Now I'm looking at time multiplied by rate. Well, that gives me total amount. So really what I've got here is the total amount of energy in minus the total amount of energy out is now equal to the total energy change for my system. And again, we've said the three types of energy that can come in or out are going to be heat, work, and mass. And because it's a closed system, there's no mass. So the only types of energy that can come in or out are going to be work and heat. So we're going to add those coming in, subtract the work out, subtract the heat out. And again, because it's a stationary system, the only type of energy that's going to change, the kinetic and potential don't change if it's stationary. So the only type of energy that's going to change is going to be the internal energy. So add the in, subtract the out, set that equal to the change. If it's a closed stationary system, this is what we're left with. Are you going to have all four of these different energies for your system? No, probably not. That's going to be in your problem statement. Look at your problem statement. Draw your system. We talked about this before. Draw your system just like a draw free body diagram. Draw your system. Draw all the energies crossing the boundary. And when you write your equation, all you have to do is for these four terms, you just only have to look at your picture. Add the in, subtract the outs. Set that equal to the change. It's a closed system, closed stationary system, that's in delta. So what are some common types of heat and work? Well, again, you guys will go on most likely to take a heat transfer course where they'll talk to you in depth about different ways we can estimate these heat values. We don't have those tools on board yet. Okay? So for us, the heat's either going to be something we can solve the first law for, something I can drag out of the second law, we'll see in a second, or it's something that's given to me where I'm solving for. Those are my main tools for heat transfer at this point. Work, on the other hand, that's a little different. Work is the application of a force applied through a distance. So that can take a couple of forms, right? So let's look at types of work. Discuss these throughout the semester. You could have electrical. You can have electrical work. Electrical power, that's W dot sub E, is equal to voltage times current. Now, if you want the electrical energy, that's going to be the integral of this W dot E with respect to time. If voltage and current are constant, if V and I constant, this is what we call DC, direct current conditions, like a battery or a solar panel, right? If voltage and current are constant, then the electrical work is essentially equal to the electrical power, which is constant. And if I integrate this constant with respect to time, then this just becomes the rate multiplied by the total amount of time. Otherwise, I need to know how voltage and current vary as a function of time. When you go on to take some sort of electrical science course, you'll know it could be a sinusoid. So if it's over a long enough period of time, then it's basically kind of condenses to a constant. It could also be an exponential type function, could be some kind of step function. But for our purposes, we're just going to be looking at DC conditions. Here's a voltage, here's a current. Given this power, figure out how much energy goes in the system, something like that. Or given the energy N, figure out the voltage and current over a particular time period, something like that. We've seen some variety of that throughout the semester. So that's one type of work that we can encounter. What's another type of work we can encounter? Well, common type of work we can encounter a lot. You could just simply have a force applied through a distance, but you could also have a paddle wheel or some other kind of shaft that's just providing a set amount of work. You could finally have what we call boundary work. So boundary work occurs when the volume changes. V2 is not equal to V1. When V2 is not equal to V1, that volume does not change spontaneously. Something has to occur to do that. Often we see this in a piston cylinder. That's the most common generic type of system where a volume can change. But it could be anything where the volume changes. That volume does not change spontaneously. A force has to cause that volume to change. And what normally drives that force is a pressure difference. So the pressure serves as our force. So again, work being the integral of force with respect to distance, what causes the force for a boundary work problem is going to be the pressure internally or externally pushing or pulling the system. I'm going to integrate the pressure with respect to volume. Now, if I integrate from the initial volume to the final volume, what I'm finding is the work out. It's the work that's leaving the system. So if the system is expanding, I will get a positive boundary work out value, because this V2 will be bigger than V1, therefore this integral will be positive. That represents work out. If the system is expanding, that's work out. The system is pushing the surroundings out of its way. It's doing work to the surroundings. If the surroundings are compressing the system, and so if V1 is bigger than V2, you'll get a negative quantity here. Right? And the reason that's you're getting negative is because the system is actually pushing into the surroundings. So the system's doing work to the surroundings. That's work in, the opposite of work out. So I would expect to get a negative value here. So expansion, positive work out, compression, negative work out, we're actually working in. So again, what does all this represent? First law, what are the different types of heat and work we might encounter? That's a little bit about those. These are two of the most common I would expect to see on problems. And I assume that's, or I'm very comfortable that's going to be accurate if you look at the homework and the exams throughout the semester. Okay, so what else here? If we look at first law for steady flow control volumes. And so I'm looking at first law for steady flow control volumes. Now, there's a couple of things occur here. Because I'm dealing with a control volume, that means mass can flow through, and I've also got to track the mass because the mass has to be conserved. So the total rate at which mass comes in minus the total rate at which mass goes out is equal to the total mass change for my system with respect to time, dm dt. Again, this is just like we saw earlier. This is in minus out. It's changed. It's a conservation law. This particular one is conservation of mass. Now, what we have here is a variety of ways you can find the mass flow rate. The the most common ways is if I know the density of my substance that's flowing and I know the rate at which volume flows. Well, density is mass per volume. So if I can multiply that by volume per time, that's m dot is equal to rho v dot. That gives me my mass flow rate. Now, am I going to know my v dot? Well, maybe. A little harder to measure. There's some ways you can maybe measure it, but the simplest thing we can probably do, and we talk a little bit about this in a fluid mechanics class, what could I measure? Well, there's some ways that I could probably measure the speed at which that fluid is flowing through a conduit into or out of a system. And if I can take the speed multiplied by the area, the product of area and speed gives me volume per time. Right? It's length times length divided by time. That's length cubed divided by time. That's volume per time. And again, we've already defined, well, I haven't defined today, we've defined throughout the semester that the reciprocal of density is what we call the specific volume. That's little v. So anywhere I've got density, I can plug in 1 over the specific volume, and that's the same thing. So again, as we've seen throughout the semester, know which v you're dealing with, what type of v value. Is it speed, volume, or specific volume? That's not changed. So this is how we would find the mass flow rate. There are a variety of ways I could find the mass flow rate, and everywhere mass comes in and everywhere mass goes out of my system. Now, there's a few things happen here. What we mean by this idea of steady flow, and in many texts, that's steady state is what they call that. If I'm dealing with steady flow, that means everything with respect to time is constant. Nothing changes with respect to time. So if that's true, then this dm dt goes to 0. We're saying the mass of the system itself doesn't change over time. We're just flowing mass through it. And basically what it means is that the total rate at which mass comes in is going to equal the total rate at which mass goes out. And a smaller subset of that, but a very common subset, is for one inlet, we often call that 1, and one outlet, we often call that 2. What I have then is m dot 1 equals m dot 2, and we just simply call that m dot. There's no reason to differentiate between the two because they're the same. So again, it's a subset. It's kind of a special case where I've got one inlet, one outlet, and it's steady flow. Then it just simplifies down to this. How do I find that m dot? A variety of ways. Depends on what I know. What do I know about the inlet and the outlet? If I know that variety of terms there, that would get me there. I only need to know those properties of one inlet at the inlet or the outlet to find the m dot. And it'll be the same m dot at the outlet if it's one inlet, one outlet, and steady flow. Now, again, we're looking at steady flow control volumes, and we're really focusing on the first law. But because I've got mass flowing, we need to spend a moment to talk about conservation of mass to get there. Now that we've discussed conservation of mass here, let's talk about how the first law is impacted. What's that look like? Well, if we go all the way back to the first law, it's E dot in minus E dot out equals dE for my system with respect to time. As we've already discussed, these are heat, work, and mass. Talk about that back here, page 3. Page 3 was a heat, work, and mass can cross the boundary. Internal kinetic and potential energy for my system is what can change. Well, if I've got a steady flow control volume, steady flow means nothing's changing with respect to time. So that means the internal, right? So again, this E system represents for the system the internal kinetic and potential of the system. What we're doing here is we're saying, well, if it's steady flow, that's going to 0. The system itself, the turbine, the heat exchanger, the nozzle, whatever it is, the system itself is not changing its internal kinetic and potential energy. We've reached a point where it's kind of operating steadily. So the system itself is not changing energy. What I have then, all that's left is changes from the inlet to the outlet. Okay. So what does that mean? Well, again, this could be heat, work, and mass are the types of energies that can cross the boundary. So let's look at those. So we'll say it's Q dot N, that's the rate at which heat comes in, plus W dot N, that's the rate at which work comes in, and that has a special name. We call that power. Power we only reserve for work rates. So this is the rate at which work is coming in, the power, plus summation across all of the inlets, M dot times, and here we're going to use an H, but let's talk about why it's an H, right? Because this mass that's coming in, the mass that's coming in has its own internal energy, has its own kinetic energy, and has its own potential energy. But because it's flowing, something has to push that energy to flow, right? So we're going to use H's because that mass has its own internal energy, but it also has the energy of the fluid upstream pushing it out of its way, right? So kind of a side note here. Why is it H value? Why not just have U down here? Well, because it's not stationary. If it's stationary, it would only have a U value, but because it's flowing, something has to cause it to flow, and that's the push of the fluid upstream or something pushing it, causing it to flow. In most cases, it's just the pressure of the fluid upstream. What causes that pressure? I don't know. It could be a pump, it could be a piston, it could be something. Something's causing the fluid upstream to push the fluid downstream out of its way. So the sum of that U and the push of the fluid upstream simply results in an H value. So the flow has its own enthalpy, its own kinetic energy, and its own potential energy, which we normally just neglect because it's negligible. Microjoules compared to kilojoules over here. But we can account for it if you like, at least mention that it's there. And then all those energies going out. So minus the heat out, the heat rate out, Q dot out, minus the power output, W dot out, minus the sum across all of the outlets, M dot times H plus V squared over 2 plus GZ. Why is 0? Because that's the change. This is the change. And we're saying if the system is flowing steadily, if it's flowing steadily, the system itself is not changing its internal kinetic or potential energy. That doesn't mean it's not changing from the inlet to the outlet. Those will change. So I've got water coming in, it gets heated up, and I've got hot water going out. The energy here will be different from the energy there for the water, but not necessarily the system. The system's flowing steadily. Okay. Yeah, this is why. Not just a U value, because it's flowing. Now, This is the kind of the most generic form of the first law we would use for control volumes. This works really well if I've got multiple inlets and multiple outlets. I need to come back here. If I've got one inlet, again, we can call him 1, and one outlet, we'll give him 2. And this simplifies just a little bit. I'm going to group the Q's and W's together. So I'm going to say Q dot in minus Q dot out. You don't have to. You can write these terms in any order, just preserve the sign. But here I'm going to say Q dot in minus Q dot out plus the power input minus the power output. And again, if I've got one inlet, one outlet, we've already set up here, one inlet, one outlet is a common m dot between the two. There's no need to differentiate it. We'll just factor it out. I don't have to do the summations I've got here because there's only one of each. And they have common mass flow rate, so we're just going to factor it out. And then I'm just going to include H1 minus H2. I'm only going to include the kinetic energy, V1 squared minus V2 squared divided by 2. I'm going to close that off. I'm going to set that equal to the change for my system. If it's steadily flowing, the change is 0. And I'm just going to simply say, assuming Z1 is approximately Z2, and that's almost always a safe assumption. You have to have an enormous system to where the change in potential energy would approach numerically the change in entropy. A lot of times we don't even consider the change in kinetic energy because it's normally joules compared to kilojoules of the entropy change. Again, it depends on the device. It depends on what we're given. If we're given enough information to compute the kinetic change, we should always do it. We talk about how we know that. Well, do I have the V's? Can I find the V's? Which normally means do I have the areas? Or if I have the areas, I can find the V's. Is it a nozzle or a diffuser? I have to. Those devices specifically change the kinetic energy, so I have to know that. Questions so far? Where do we go from there? Well, that's in and out of the first law. And there, if we look at the second law, what do we do with that? Well, the second law in its purest, rawest form is a differential inequality. We're going to say that the change in a quantity we call entropy, that's an S value. Change in entropy is always greater than or equal to the amount of heat transfer, that's a dq, it's a soft d if you will, divided by temperature. An exact differential. Because we don't know what's at play for the heat transfer. Normally it's just the temperature is the main driving force of heat transfer, but it could be other parameters. Sometimes they're difficult to determine. Again, most of you will go on to take an entire junior level engineering course in heat transfer. And if you do anything serious with it, you'll go on to take graduate level courses after that. Heat's a really interesting topic, but for an intro thermodynamics course, we're going to be very, very simple about what we do with it. But the good news is again, I'm not expecting you to do much with an inexact differential here. Let's talk about what I could expect you to do with this. Okay. Well, the first thing is most of the time we're going to look at a process from state 1. 2, and what that means, I'm going to integrate both sides of this equation from state 1 to state 2. Well, the integral of ds is just delta s, s2 minus s1. And then what we normally do is rather than deal with this inequality, we're going to set this equal to, we're going to create an equation but preserve the rule. Well, what do we do with this heat transfer? Well, it depends on the situation. So we're just going to leave it as the integral of dq over t right now. But again, to preserve this inequality, I've got to do something to preserve the rule. And what I do is I just say, well, add to it the entropy generated. Because what our good friend Klaus is telling us here, Klaus is the one that made this determination. And he's basically saying that the entropy is always increasing. There's always more entropy. There's entropy generated. So that becomes the rule. So we expect that the entropy generation is always positive. There's more entropy than when we started. Therefore, nothing is reversible. We can't get both the system and the universe back to their original state because there's now more entropy in one of the two of them. I can get the system back to its initial state. I can get the surroundings back to their initial state, but not at the same time. Because there's always more entropy now than when I started. If the entropy is conserved, if there's no entropy generated, we call that reversible, meaning I can get both the system and the surroundings back to their initial state at the same time. If there's more entropy in either one of them, I can't get either one of them. I can't get both of them back to their initial state. So what do we do with that? Well, we talked about determining this delta S. How can I find that? Well, we said I can use property tables for water in R134, as we've already seen. And by the way, this is total entropy. You can also look at this on a per unit mass basis. That's one of the things that we learn in a thermodynamics course is that most equations can take on a variety of forms. This one can take on a per unit mass basis where I divide both sides of this equation by mass, and I've got little s2 minus little s1 is now equal to this integral of d little q over t plus little s gen. And I know my s's look the same whether they're uppercase or lowercase. Again, the lowercase is the one that's been divided by mass. We could also look per unit time. We've seen this with both first law and second law problems. Right? Sometimes it makes more sense to measure this over a period of time. Well, what I can do there is I could take m dot times little s2 minus little s1 and say if that's equal to the integral of d big Q dot, excuse me, over t. Plus, then you could say this a variety of ways. I'm just going to say big S gen dot. You could take little s gen multiplied by m dot. That's basically what big S gen dot is. That's the rate at which entropy is getting generated. Entropy generation per unit time. Right, so again, we've talked about how do I quantify this? What do I do with this guy? Well, again, property tables for water in R134 will give you S values. Same rules apply as we use for U's and H's. Okay. I could use the second law itself, right? If I can quantify this side, that tells me that side. So if I use the second law itself, right? What are some common things we can do with that? Well, if heat is transferred at constant temperature, which is the most common thing that we're going to do with heat transfer in the second law problem here. Right? There's two things I'm going to ask you guys to be able to do with this thing. One is either deal with heat transfer at constant temperature. Well, and that what happens then is, again, what the heck do we do with this partial integral? Well, there's not much, but this is one thing. If the temperature is constant, it comes out of this integral. Then I'm just integrating dq. Well, if I integrate d anything, it becomes that anything. So the integral of dq is no different. This becomes q, and what we do is we say this is q net in divided by that temperature. Because we're saying the qn is positive and the q out is negative. So it's basically q net in divided by temperature. And that's how most texts will present this. They don't present it as this integral. I don't mind that yours does, but it does mean we need to talk about what the heck we do with that. This is the most common thing we'll do with it. The next most common thing we might do with it is if adiabatic. Again, what happens if we add up a whole bunch of zeros? That's what we're doing when you integrate, is adding up a whole bunch of little tiny slices. If I add up a whole bunch of little zeros, I still get 0. Okay, so what else do we do with this? Well, those are the main two things that we might do with this integral dq over t. Okay. So what do we do then with the s gen? Well, the common thing is I'm trying to solve for s gen, right? So I'm trying to determine is the process possible, reversible, or irreversible. But if they somehow told me that it's reversible. If they told me the process is reversible, that means it's not generating entropy. It's the best possible version of the device, or the best outcome I can expect from the process. So if there's something in the problem statement that tells me, hey, look for the best case scenario, they're telling you that's the scenario where it's not generating entropy. And so you can go back to this equation then, any form of it. If I can deal with this guy and I can deal with this guy, then I know this other scenario. So those are the main things that we're going to do with this equation, at least the right-hand side, is what are we going to do with that integral dq over t? Well, there's two main things I can do. What am I going to do with the entropy generated? Either I'm looking for it or they've somehow told it to me. And the most common thing they're going to tell me about it is that it's reversible. Therefore, it's zero. So if it's adiabatic and reversible, right, if this is zero and this is zero, then it's not changing entropy. We call it isentropic. Adiabatic, we'll write that. We've written this several times, but I don't mind writing it again. It's important. Adiabatic, adiabatic, there's no heat transfer, plus reversible. And that's, I'm going to draw an arrow here. I'm very deliberate about this. I'll draw an arrow and say that is what we call isentropic. So we're saying that if this integral dq over t equals 0 and s gen equals 0, then s2 minus s1 equals 0. I've drawn an arrow. Discuss this. I'm not going to spend too long on it, but it's worth mentioning. This can be negative, right? When would this be negative? Under what circumstances would I expect this to be negative? What's that? If it's losing heat, right? If it's losing heat, or if I'm losing more heat on one side than I'm gaining on the other, or the heat divided by temperature I'm losing plus the heat gain divided by that temperature, if the negative quantity is larger, right? There's a lot of scenarios, but they all require a loss of heat somewhere, right? So if there's loss of heat occurring somewhere, that loss term is going to have a negative sign on it. So it's possible that this is negative and this is positive, and it's possible that they're equal and opposite, and therefore this is zero, right? That's the reason for the arrow. Adiabatic and reversible tells me it's isentropic. If it's isentropic, that does not tell me it's adiabatic and reversible, right? This could be negative and this could be equal and opposite, and therefore this is still zero. Hence the error. Okay? It's a very specific scenario. The best example I can give you is a phone charger once it's kind of operating normally, once it's kind of settled down. It's losing heat, right? That phone charger is losing heat, but you want it to, if it's kind of hitting a steady state point, some kind of equilibrium, it's going to lose heat, but if you think about that phone charger, the entropy of the phone charger components are going to be a function of temperature. So if it's losing heat at a constant temperature, then it's basically losing entropy at the same rate it's generating. So it's not at all an unreasonable thing to have that scenario where this is the negative of that, or I guess this is the negative of that, and therefore it's isentropic. So it's not an impractical scenario to say, well, you're never going to encounter it. No, actually, it's not too hard to find examples of that. Hence the arrow. If I know it's isentropic, I don't know it's adiabatic and reversible. If I know it's adiabatic and reversible, I know it's isentropic. Okay, that's critical stuff we got to talk about there. Let's talk about what else is left. So we talked about dealing with this second law equation. We said, well, this is going to be the Q over T. This is either 0 or what I'm trying to solve for, most likely. What about the delta S? Other ways I can find delta S. Well, we said property tables work really good. It's isentropic. This gets you from state 1 to, this gives you a second property to get from state 1 to state 2 sometimes. Another thing that allows us to determine delta S is the Gibbs equation, the Gibbs free energy equation. That's another tool we can use under certain circumstances to determine delta S. The most common of those is for ideal gases. So for ideal gases, the entropy change, these are little s's, little s2 minus little s1, is equal to the integral from T1 to T2 C sub V dt over T. This is plus R ln, and this is ratio of specific volumes, little v's. Okay. And what we normally do is we normally say, well, this is approximately equal to, if I pull C sub V out as a constant at the average temperature, then this becomes C sub V average ln T2 over T1 plus R ln, and also the ratio of V2 over V1. So that's an approximation. It's a reasonable approximation. Again, this form works really well if I know my ratio of volumes. If my ratio of volumes, if my volume is constant, then I've got the natural log of 1, which I think is 0, right? So a very handy thing to use for probably closed systems, especially rigid containers where the volume doesn't change. So this actually works out pretty simple in that case. That doesn't mean I can't use this other form. I can always use either form. Delta S is also equal to, there's another form where we say, well, it's the integral from T1 to T2 of C sub P dt over T. This one has minus R ln, and the ratio here is pressures, P2 over P1. Just like we did earlier, we could also say this is approximately equal to C sub P at the average temperature. So I'm going to pull that out as a constant out of the integral. That's just integrating dt over T. That just becomes the natural log of T2 over T1, still minus R ln P2 over P1. Again, this form is probably more practical for control volumes, where I can probably measure the pressure at the inlet and the outlet, as opposed to a closed system where I might be a little harder to measure. I could still measure pressure in both cases. It's a little harder to find a specific volume of the flow in a control volume, not impossible, especially with the ideal gas law. But normally, I'm probably going to use this form for control volumes, normally for closed systems, but I can use them for either case if I'm dealing with an ideal gas. What else here? And we did say that if you don't like, again, to use C sub P, we've seen this earlier. To use C sub P average, that means I need to know both temperatures. If I don't know both temperatures, I'm going to have to guess and check. I'm going to do a quick iteration to get down to using basically the table as my equation relating C sub P to T2. It's going to require a guess and check. However, there are table properties. I call them S degree. I think they're called S circle. S circle 2 minus S circle 1 can take the place of this integral C sub P dt over T. And I still need to minus out here R ln P2 over P1. And that's another way that I can find S2 minus S1 for an ideal gas. These S circle values are property tables of a function's temperature. That's an actual equal sign, not an approximation. So any of these work. They're all the same equation. They all come from the same place. They're just derived a little bit differently. It just depends on what properties I have. Which one we'll use. They all work. And that will give you an approximation for the left-hand side of this equation. So I'll give you this delta S values, and that'll allow you to use it in conjunction with what you know about this side to get to a solution. If it's a solid or liquid, again, phase needs to be constant because I'm going to use specific heats here. But for solids and liquids, assuming the phase is constant, then S2 minus S1 is approximately equal to C sub P average ln T2 over T1. And that's it. Again, your text for solids and liquids likes to use C sub P. My preference is just a standard C because there's no difference between C sub P and C sub B for solids and liquids. That's an entire semester in 75 minutes.
You said
Well, it's more about which of these properties can you get, right? The question is which one of these is better for which, and it really comes down to which of these properties are more realistic, right? If I've got a closed system, well, let me put it this way: if I've got a control volume, I'm probably not going to know the specific volume of the fluid coming through. I'm going to have to estimate it, which is possible. But if I've got a control volume, I'm probably going to be able to put a pressure gauge at the end of it. A lot easier than I could either take a sample and measure a specific volume or somehow approximate a specific volume, right? As opposed to, let's say, a closed system. If I've got a closed system, it's a little more likely I'm going to be able to find the specific volumes. Either equation works. They come from the same place. So if I've got an ideal gas, either equation works for any type of system. It really comes down to which properties do I have on hand that I can get to easily. That's a good question. Other questions?
So go back to like chapter 1 and I'm gonna put you this word thermometer.
Okay.
Problems. Is that something we'll see? Or is it kind of in that like set where you pick?
Very good question. Manometer problems. I'm not going to put a manometer on this final. Okay. I do that for a variety of reasons. It's not exactly one of the learning outcomes that we discussed earlier, right? Manometers allow us to find changes in pressure. Okay. It's important we understand changes in pressure within a fluid is related to the change in height in the column. But this is what I know. Between fluid mechanics and then other courses later in just about any engineering discipline, you're going to get a ton of that concept, whether it's manometer specifically or any other concept. So me personally, I don't think it's necessary to put it on a thermo final because you're going to see it again. And again, it's not specifically called out in our learning objectives. That's a good question. You need to have some understanding of what pressure is at this point, and manometers help to do that. And I think that's kind of the purpose that it's served for us early in the semester. That's one of the very few things in this class I can point to and say, yeah, we probably won't do too much more with this, but it's good to know what pressure is and what it represents. Because we do use pressure throughout the semester. Other questions? I'm going to pause, or I'm going to stop recording then from there, and we can figure out what we're going to do after that.